All right. Well, thanks everyone for your attention today. I appreciate the opportunity to come speak. What I'll kind of shoot to summarize on a high level, and then we'll kind of go into some specific research results related to 3 projects that were recently funded through NREC, and a lot of the preliminary data that led to identifying those projects as priorities. So we'll go over specifically on nitrogen rate trials and some output of that. I'll talk about a newly initiated wheat project that's looking at nitrogen, phosphorus, and sulfur management. And then I think the lion's share of the time will probably be spent on the phosphorus and potassium calibration studies, because I think that's got a little more recent research results that are a little more fresh maybe than what you'd seen before. I did want to highlight, Andrew had this tactic last year, and I did want to share, I think the ability to leverage a lot of these projects and funds when competing for federal or other funding sources is really something that I know the PIs that are funded through NREC really take advantage of, and it's something we've done as well since the last 2 rounds of projects that we've been able to secure around $6 million to leverage the investment that NREC made through the funders that are on the screen. And I think that match is something that we should really target for bringing dollars to Illinois specifically to do soil, in my case, soil fertility and nutrient management research. But a lot of this can really be, I'll say, an engine to start looking at other components. Maybe the applied part of the project is funded through NREC, and we're going to some more basic research relative to nutrient cycling, in my case, with some federal projects. So I think that's a target that we certainly have when we think about projects we're developing and targeting NREC funding for. The first project I'll discuss is refining 2026 corn nitrogen rate recommendations. That's not necessarily the title of the project, and I'm going to kind of phrase a lot of the results that I'll share today in context of 2026. When we think about economic scenarios and decisions that farmers are having to face, specifically the farmers and agronomists that are related to the tonnage fee that goes to support NREC projects. I'll kind of do a slight dive into nitrogen here when we start looking at results from trials around the state. But I think and this kind of maybe ties into a little bit of what Ben had mentioned, and I think what Lowell and Zhangji will follow up with as well, is that the real challenge when we think about statewide or even course regional interpretations of response trials to nitrogen rate, for example, that I'll share in a little bit, is that this variability of soil and supply is just so large and unpredictable in a given year that we really haven't been able to kind of tame that tiger, so to speak, or understand how we can have some predictability. And you kind of see the textbook understanding and discussion around organic nitrogen cycling and nitrogen transformations in the soil. Some of these concepts and processes within nitrogen cycling, we're kind of taking the applied work that's being done and funded with on-farm trials, and then trying to look at soil and plant end cycling to answer, for example, what's the role of ammonium when we look at release of ammonium from the interlayer of clays, and we're doing that with potassium as well. Some trends across the state when we think about the nitrogen rate trial program that Dr. Nafziger had started and that we're continuing on. These 3 lines or 3 clouds of data, so to speak, show the yield at the optimum nitrogen rate, the yield increase from nitrogen applied, and the yield at 0 nitrogen applied from 2006 to 2024. I'll move into the 2025 data in a few slides. But this is something that gets brought up a lot, especially regionally, is our corn crop requiring more nitrogen as yields increase over time? Certainly when we think a given plant's demand for nitrogen relative to the production of biomass or harvested biomass in grain, the nitrogen demand is likely going to go up. Now there's been some improvements, good things happen when you breed for yield in terms of nitrogen use efficiency, but these are the trends I would say that are fairly constant in different parts of the north central region or corn belt. The challenge is really understanding if soil is going to keep up with these increases in nitrogen demand. And largely, there's kind of a yes, no, maybe answer, unfortunately. When we look at the yield at optimum N rate, we certainly do see that increasing over time. The orange squares are showing the yield increase, or essentially the yield you're gaining from the difference between the control plot and where yield was maximized and then price and ROI were considered. And you can kind of see a parallel there within the orange line and the squares and the the triangles and the hash line on top. In general, when we look at these increases, whether it's the yield at optimum nitrogen rate, the increase in yield when applying nitrogen, or even the control yield, there's slight increases over time. Now the yield with 0N is kind of a flat line, and this is statewide data. So there's some regionality to all this, but certainly this begs the question, what are the other factors that we need to be considering, whether it's management or some type of diagnostic tool to understand where the soil can keep up and where it can't, essentially. I'll go into a little bit of background on the economic and yield analysis and how the system really is supported around the state. When we look at the trials that were run this year, we certainly saw a nice spread around the state. The system itself is supported by hundreds of trials that have been run through the last 10, 15, 20 years. And this is really a data-intensive approach. Now, certainly, if you've seen me talk in the past year and a half, I'll say, we use this kind of a large data approach to make predictable decisions relative to nutrient management and fertilizer and soil management specifically. And it really does consider a long-term approach when looking at aggregating data over time. The challenge is representing all the different combinations of soil and growing season conditions and crop demand in a given year. And so filling the gaps between those orange points on the map there is something that we're certainly working with Dr. Guan's group and trying to interpolate between different soil and cropping systems. Interestingly enough, when we look at a lot of the trials, one of the most important things is that we do have true controls on many of them. Some there's a starter rate, some there's a fall P applied, and so we do have some nitrogen applied at the lowest treatment. But what we can really do is look at and isolate the response to nitrogen specifically, and that's a really important part of the coverage around the state. The third bullet, I think, is really important when we think about the economic scenarios right now. There's a philosophy that, or maybe an interpretation that there's a big difference in yield values between maximizing yield in a given study or the yield that maximizes ROI. And we found this in 2025 across 73 response curves, it's about a 1.34 bushel difference between the maximum yield in a given trial and the yield that had the highest economic return. So it's kind of a fallacy that you're leading to a large yield suppression when you think about ROI. Now that does change in continuous corn systems versus corn following soybean. There's a little north to south gradient when we look at the responsiveness of specific soil or corn and grown in specific soils to nitrogen. But in general, there's two components to improving ROI. There's an input adjustment and a yield adjustment or maintenance. And they aren't necessarily equivalent. So if we're talking to farmers about a improved management relative to their ROI for nitrogen rate, for example, the yield component of an improved ROI is not very large. We're not dropping yield that much. But the improvement through an input reduction, and this year it was about 10 to 18 pounds of N, from the maximum yield down to the maximum ROI, so to speak, is really where that improvement in return, economic return, comes from. Now I'll get into a few slides with some of the response curves from trials run this year. These are the corn following corn trials in the northern part of the state and the central part of the state. Interestingly enough, since the first part of the year, I've gotten 8 emails saying we need corn on corn nitrogen recommendations for the southern part of Illinois. I see Laura in the crowd. We've talked about this a little bit. That was something that we did drop from the NREC calculator last year, solely because there hadn't been any corn on corn trials run since 2016 and before that 2010. So we were working with a little bit older data, and we wanted to build that up before providing those interpretations. And I'll show a table summarizing that a little bit later as well. But in general, this year, when we think about kind of a gradient across the state, we had some really strong regionality in crop growing conditions and responsiveness to nitrogen. If we look at just the data in aggregate in the region, corn following corn in the northern part of the state and central part of the state, the optimum N rate was around 191 pounds. This is at a 10 to 1 corn price to nitrogen price ratio, 191 pounds of optimum N rate at 248 bushels. I put the NUE terms up there to bother my PhD student Blake, who's in the crowd somewhere, because this is just the pounds of N per bushel applied. You'll see that most of these NUE terms I'll show in this slide and the next slide, none of them are approaching, or only one of them is above 1. So this idea that kind of a yield factor applied to an expected yield and then calculated nitrogen rate really isn't something that holds true. And I think one of the things that's important is that in a lot of our farming systems, we're well below maybe what and the old adage was for some yield factor of determining a nitrogen rate. If you look at the corn following soybean trials, we saw a trend that I would say is fairly consistent when we look at optimum nitrogen rates in given latitude across the state. The northern part of the state probably had a little more advantageous moisture earlier in the season and then into later part of the season. We did see some some less responsive sites in the northern part of the state where we were really maximizing yield with a fairly low optimum nitrogen rate. But I would say this pattern from north to south is certainly something that's been pretty consistent, and I would expect to continue. You'll note the variability in yields and responsiveness to N in the southern part of the state, really due to planting date adjustments, drought considerations that occurred, and so we did see some very strong growing season effects in the southern part of Illinois. This would be just a summary of 2025 data. So this isn't what's coming out of the corn nitrogen rate calculator. This is just for 2025 data with specific pricing scenarios. So essentially going from half a dollar per pound of N as we'll say spring anhydrous over to 3 different scenarios for UAN applied in the spring. And I think when you look at, again, these patterns from left to right, from top to bottom, you would expect that fairly consistently across the state. The challenge then, and something that's really exciting going forward, is the amount of metadata we're collecting from a lot of these trials, whether it's soil, plant uptake data, crop canopy sensing data, and collaborating with many in the room today and then on campus and across the state as well to get that. You'll notice the continuous corn line there on the bottom. And right now we're kind of recommending to look at the corn following soybean data for southern Illinois, only because that data, there was a much less of a spread with previous crop in the southern part of the state. Usually because there's the mineralization potential is a little bit adjusted in the south compared to the north. And going forward, so the data will live here on as we finish actually this week updating the 2025 data and getting it onto the corn NREC calculator. This is where the data kind of lives and breathes as you can interpret it with different scenarios of region of the state, previous crop, and pricing scenarios as well. And I think I showed this slide at a few talks this winter, but certainly this is the case when you're looking at moving from a cheaper input to a more expensive input. The scenario here is for northern Illinois. This is data from 2013 through 2024. And corn price held constant at $4, and then an increasing nitrogen price from half a dollar up to 80 cent N. And certainly you can expect to see the profitable range of optimum N rates reducing as you go from left to right. But again, the difference in the maximum bushels produced in a given trial is really not very extravagant. It's not that large of a value, and so that's something that I think is important. When you look at the percent of maximum yield obtained at the MRTN rate, you see a shift only from 98 to 97%. And we can look at this a little bit differently when we think about the distribution or frequency of optimum N rates over time or over space as well. When you look at, we'll say, cheaper nitrogen or relatively cheap nitrogen at 40 cents per pound on the left, this is again in a $4 corn scenario, most of the sites are frequently popping up between 150 to 200 pounds of N in terms of providing the optimum fertilizer N rate there. You'll see that shift to the left when we get to more expensive nitrogen. Not really surprising, I would say. One of the studies that we did start in the fall of 2024, and actually in kind of the summer of 24, was looking at the interaction between tillage and previous crop, optimum N rate, and yield. I see these studies established around the state as kind of calibration studies where we necessarily can't do all the 4R factors on every on-farm trial, but we can use these static long-term studies at the research stations to guide how things may be adjusted if indeed that's the case. Certainly there are states to the west that do consider long-term tillage practices and nutrient cycling. We really haven't seen the ability to do that yet, but it's a question we get a lot. If we've been no-tilling for 25 or 30 years, is the nitrogen cycling within my soils to a different degree than our neighbor's field that's fall chiseling and spring cultivating? This is just data from 2025 across 3 sites. This is showing the optimum nitrogen rate different tillage systems and then previous crops. One of the important things this year was that we really didn't see much of a difference in the corn following soybean. Now, these sites had just been converted from no-till systems, from conventional tilled systems to the 3 tillage systems you see on the screen. So we've got a little bit of a honeymoon period, so to speak, when we're dealing with the conversion from a conventionally tilled system to no-till. And I would expect to see some of the trends you see here, but we'll be continuing that going forward as well. So this is kind of a wrap-up of some of the nitrogen management components that I shared, and specifically moving into 2026. I think these are important factors to consider when we think about the difference between the yields that we're maximizing bushels per acre in a given site in a given study versus the yields where we're maximizing economic return. They really don't vary much across the board. There's certainly things like timing and placement that can be adjusted, but in terms of really predictable or consistent adjustments to optimum N rates, we really don't see much difference within the timing unless you're comparing a straight fall to spring timing. Then there's maybe a little more of a consistent reduction in optimum N rate. But really the adjustments that I would say are important are to look at your expected corn price sold or price that you're working with, and then adjust for the nitrogen price of the bulk of the N that you'd be purchasing. So that's kind of a snapshot on the nitrogen rate trials that were run last year and some of the trends that we've seen. I have a few slides just summarizing a new project that was started. We had some 2 site years of preliminary data that we accumulated in 24 and 25, and so I'll go into those in the next 2 slides. So this project is really designed to look at a few things, specifically nitrogen management for winter wheat, sulfur management, and then phosphorus as well, really geared towards developing a nitrogen rate calculator for wheat within Illinois, or a calculator that can be queried and looked at relative to region of the state and pricing scenarios. There's a table in the agronomy handbook that kind of does that right now, but we're looking at a few more options of intensively managed wheat. And so the sites that were done in 24 and 25, you can kind of see in the blue marks, they were in Pike in Piatt County, so central Illinois sites, but then the sites that were established last fall, this is a collaboration we've got with Giovanni Presefontes and John Pike. When looking in the southern part of the state, I think we're getting a good representation of some of the wheat acres down in that region. These were trials that were run again 24 into 25, and I would say the major, I'll say, consistencies that we saw where the optimum N rates were pretty comparable to the table that's in the agronomy handbook, but a little bit higher relative to the organic matter within these specific sites. I would say the N demand in the spring and growing season of 25 was a little higher than what the previous interpretation would have suggested here. You can see there was a little bit of a lodging effect over at the Ore Center in Pike County. But essentially, when looking at the optimum N rates and yields, the optimum N rates range from 120 to 130, yields from 101 to 119 bushels per acre. So this is kind of where I'll spend a little more time just going through some of the research results relative to, I'll say, recommendation updates or preliminary indications of maybe a direction that we're headed. This is a project that's designed to look at calibration of soil test phosphorus potassium around the state, but also in relation to things like source rate and timing and tillage effects within those given sites. There's really about 8 steps that need to undergo to improve or revise a phosphorus and potassium recommendation within a given state. And I was fortunate enough to do this in grad school in Iowa and just finished doing this in Wisconsin. And so this is always in the top of my mind. There's kind of a pipeline of work that has to happen to get to a certain point where you have very predictable and consistent enough data to say this is the direction where things, it looks like they should head. And really within these specific steps, you're looking at different components of identifying where soils will and will not respond to P or K. The calibration part is really, I would say, the lion's share of what this project is looking at. It's the given optimum rate relative to a soil test level and your application strategy. The third bullet is really important. It's in the background of almost all Midwestern P and K recommendations, and that's the buffering capacity or the buildup and drawdown coefficients. You might notice that as 9 pounds of P2O5 per pound of soil test P, 4 pounds of K2O per pound change in soil test K. I will say there's a lot of recent research that we've done in our group to say that these certainly aren't static numbers. They changed, and the goalposts shift depending on your initial starting condition, if you're building up or drawing down. And this is kind of some more basic kinetics of nutrient management, but this has big implications for recommended, specifically phosphorus rates in different regions of soil test phosphorus that could be susceptible to P loss. And so when we look at the current agronomy handbook source data, and I think Dr. Margonaut shared this when talking about the correlation part of his project, looking at identifying critical levels of soil test values. Interestingly enough, really a lot of this data, and we've now kind of combed through the original data that came from Roger Bray at the old soil fields across the state. A lot of this data was kind of earliest 20th century. It was shifted a little bit in different versions of the Illinois Agronomy Handbook with no real supporting data to say what's the next step. One of the quotes that I really like from one of Roger Bray's papers, and there's a term called a Mr. Ball unit. Essentially, instead of using bushels per acre or relative yield, they kind of used a normalized production number that looked at plant productivity or yield productivity. But essentially he says, as for example, if we get to 300 bushel corn, we should probably do something a little bit different. And even down in the bottom paragraph, he says, these values probably need to be recalculated if we get over 175 bushel corn in 1948. So I think there's precedent for working through this to a degree to represent our current crop production systems. And when we think about this work in relative to water quality outcomes, the best chance that we really have at reducing in-field P losses is to identify those high testing soils where they're not going to respond to P. This has been shown again and again, and this is work that I worked on in Iowa, looking at dissolved reactive phosphorus loss in surface runoff relative to soil test P, P loss with tile drainage relative to soil test phosphorus. Overwhelmingly, if we can manage our phosphorus in our soils in an agronomic context, we have good environmental outcomes that usually lead to that. Now, there's an important terminology and clarification with all this before we get into some of the results from the research so far. When we talk about things like critical levels and areas that are responsive or not, the maintenance range, or the range on the right between the two green bars or blue bars up on the projector, the maintenance range or those boundaries is not the critical level. The critical level is where those red curves, they start to flatten off, and you'll see certainly a different one for wheat phosphorus than you expect for corn or soybean. But this is really important that when we're comparing these responsiveness, these values where you'd expect response or not relative to soil test level, we're really comparing those that third column of letters. And so that's important when we kind of learn this looking through the original data. When we look at the critical levels that I'll share here, we're really relating them to that 20, 30, and 38 value, not necessarily the 40, 45, and 50 value. So this is a snapshot of a summary of the project that's underway that was funded and started in the fall of last year, but we're fortunate enough to have collaborators and a momentum to produce a lot of data prior to when the project started that was funded through NREC. So we're looking at corn and soybean response to phosphorus and potassium in conventional strip till and no-till systems. The tillage system isn't represented at every site. And then we're also evaluating combinations of application strategies and there's around 24 site years of data that are produced every year with multiple treatments at each site. This is a collaboration between our lab, Precision Planting, and Cropsmith that are running some of the sites, and we've got two master students working on this, Franco and Jenna. I really think this represents one of the larger efforts to work on soil test P and calibration around the state, or for a given state specifically. I'm excited to see the amount of data we can produce in a given year. Interestingly enough, when we kind of compare the sites that we're focused on and targeting, we see some similarities of where the original data came from. On the left are the soil fields where a lot of the data that Bray interpreted came from. And our goal is to try to represent a lot of those soil associations as well. So when we kind of look at quick summaries of the interpretation of soil test levels and whether we're seeing responsiveness or not. This is the relationship between soil test phosphorus and relative grain yield, or response to phosphorus. Because at the end of the day, we need to know what's the predictability of response to phosphorus relative to the soil test level. This is data from 2023 down to 2025. You can see there's around 484 points on the graph that are leading to this relationship that you see there. The data that we saw so far, critical level would be 15 to 21, and the agronomy handbook numbers are 15 to 25, not necessarily a big difference. These are, I'll note, the same soil test methods that we're evaluating. The 15 to 20 essentially represents the median point between the critical levels would actually be 10, 15, and 17. And so this is something with a terminology that I think is important to piece out, that third column of numbers in the agronomy handbook is actually what we're looking at as a differentiation between responsive or not responsive. And the statewide was 18 in our data set. If we look at potassium, there's some similarities and some differences as well. And so when you think about the range that we've observed, or where that line starts to level off relative to response to potassium, was around 136 parts per million. Now this is statewide data. I'll show the data broken out into some different subregions in a second here. But when we think about the comparison at 130 to 150 parts per million of K, it's really not that different. Now, one of the most important things in identifying an interpretation of soil test phosphorus or potassium, or soil test levels in general, needs to be the probability of response. And it's really kind of an inverse of the yield response to phosphorus in relationship with soil test P. So if you look on the figure on the left, you're looking at, again, the responsiveness to phosphorus relative to the soil test level. And on the right, you're looking at the probability of a yield response to phosphorus relative to soil test values. And you can see how it's in a fairly sharp shift down until we get to about the critical level, or around 20 parts per million. And then we start to dip down into 30, where we're kind of reaching an asymptote or a flat line. If we look at the data kind of split out into different regions, I shared some of this information at the IFCA convention a few weeks ago, and we got questions about, all right, we've seen state data and information, now can we break those out into supposed subsoil P supplying power maps or CEC regions? I'll note that Dr. Margonaut's sort of doing a lot of work and really is I think, pulling apart the pieces on understanding subsoil stocks of phosphorus and potassium, and understanding the spatial variation around the state. We just simply broke this out into the regions relative to the agronomy handbook, and really when those values were developed, it was really looking at things like lust thickness and kind of more inherent soil properties that were seen around the state relative to kind of soil surveying approaches. But when we look at the pattern, now there's some caveats here. We saw critical levels of 12, 22, and 39 parts per million in the high, medium, and low subsoil P supplying regions. Now we're missing a little high testing data in the high subsoil P supplying power region, and we're adding that into 2026 sites. But when you see this gradient, I think it probably represents more of a growing condition scenario than a subsoil P supplying scenario. I note that other states that had subsoil P or K considerations dropped them in around 2012, 2013, only because they're just not very predictable. So I think when we think about regions around the state, it's more about kind of inherent growing conditions than subsoil stocks. And this would be how the data breaks out relative to a cation exchange capacity break of around 12, which is currently used in the handbook. And the interpretations make sense. The critical level when you're dealing with a higher cation exchange capacity, silty clay loam soils, was around 141 parts per million, and below 12 was around 124 parts per million. The most important thing when kind of working through all this, and I know this is a lot of data and a lot of interpretations that we're working through, but the purpose of all these exercises is to really look at responsiveness and relationships between soil, fertilizer, and yield in many different ways. And if a lot of those different approaches to evaluating responsiveness coalesce and said this makes sense in a management context, in an economic context, and reduces the susceptibility to losses, that's kind of when I think you're in a sweet spot for understanding that you're making progress and have really justifiable recommendations that support really the economic interests of farmers to a certain extent, but also the environmental loss concerns that are there, specifically with phosphorus management. These are the optimum rates for phosphorus and potassium in corn and soybeans across the responsive sites within all these trials. One thing that's important with these optimum rates is that they're not considering a build or a drawdown component. This is just what the annual crop needed. You can kind of think of this as a different method that's used in some western states of a sufficiency range. This is what the crop needed in a given year. So if you were building up soil test levels to a higher degree, usually these rates would be higher if you were wanting to do that. But in certain terms of maximizing yield, these were the rates that were taken. And I think that's an important piece to break apart. Right now we kind of look at crop removal and then build components of fertilizer recommendations. There's not a lot of evidence to show, does removal equal the optimum P rate, the optimum K rate? Now if you look at these values, if you've dealt with grain removal and grain nutrient concentrations, these aren't too off of what an adequate yielding crop would be removing anyway. So I think those numbers do coalesce to a certain extent. But I think this is a really critical point, because with these values, and as we start kind of give more rigor to this approach, will allow farmers to say what's your risk aversion of applying phosphorus and potassium in a given year, in a given economic scenario, and how can you use the interpretation of these results. I'll go through two more slides quick. I see David's got the shepherd's crook up here. So this is again an important point of this whole process. Again, I mentioned there's 6 to 8 steps of improving these recommendations or refining them. And one of them is looking at the build coefficients. So I talked about how this pounds of fertilizer per part per million change is in the background and baked into a lot of recommendations. And what this is showing is that it's relative to your initial soil test value. So instead of a straight line of a fertilizer recommendation relative to where you're starting off in your target soil test level, it's more of a moving target of essentially when you get more P in the system, it takes less P to increase soil test levels. I think logically a lot of farmers would say that if they're talking about their build programs or maintenance programs. But this is kind of in the background. So you can see that the pounds of P2O5 per part per million go from 32 to 22 to around 10 as you're increasing your initial soil test level. These are all below the critical level, moving up towards the maintenance range. The last thing I'll show is something that we've kind of had communicated a lot. I talked about relevance to 2026, is that I've gotten a lot of questions around using base saturation for potassium recommendations. And I know there's been a lot of information shared around the state relative to that. We have not seen an ability to make a K recommendation off of base saturations. If you're hunting for 3, 4, or 8% base saturation of K, you're going to be paying for a pretty high potash bill. And so what we've seen is soil test values, specifically soil test potassium, predicting response to a much greater degree than base saturation K would be able to. Now this is just an example of some of the, I'll say, relevant hot topics that'll come up that we can answer with this long-term work, and I think have a lot of relevance to farmers and agronomists around the state. All right, these are some preliminary kind of indications of the P&K research. I don't need to read everyone up there for you, but if anyone wants these slides, feel free to reach out and I'd gladly share them. I'll end there to make sure hopefully we keep on time. Thanks, David, I appreciate it. And I'll take any questions.
Do we have a question? Seeing none, thank you.
All right.